So just before we start on the carbohydrate hypothesis lecture, I got a couple of questions from online people. So the first question is, Rob Wolf recommends taking large amounts of fish oil for overweight people initially, like you said. He said that they have large fat stores of omega-6 and take the fish oil to balance that until they're in better shape. Just to clarify, you don't recommend this and just recommend taking the 2 to 3 grams a day. That's right. I prefer the take all of the omega-6 out of the diet and, tough it out for a while. If you really don't want to do the mega dose fish oil, it's probably not necessary. It might help, it might not. So it's not something that I personally recommend. Just like the 2 to 3 grams a day, I think is fine, and just tough it out for the fat loss while that's going on. Then we have another question from Drew. Is it true that before bulking, you should lean out first in order to reduce estrogen levels? If so, what are the mechanisms behind this, and how lean should one get before starting to bulk up? What I would say there is that if you lean out before bulking up, you are actually going to be in a better metabolic state. You are not going to be quite as likely to store fat in your fat cells, which is a good deal for you and will give you a better chance at increasing your muscle mass. The one caveat, though, is that these bulking up programs are really popular. I'm just at the end of a mass gain phase right now. I eat twice a day, and I'm about 7,000 calories a day. I'm probably the fattest I've ever been. Maybe have a little bit too much fat around the waist that I'd like. So you will gain some fat mass, whether or not you like, during these mass gains, but you will also gain a lot of muscle if you mostly stick to a ketogenic diet, kind of dial back on the Metcon, you can eliminate it if you want, and lift heavy. So the ketogenic diet, lifting heavy, having a good metabolic state, being fat adapted, making sure that you don't have any insulin resistance and whatnot because of excess carbohydrate consumption, is really good. But you will put on a little bit of fat mass. So I was always stuck at 165 pounds. I'm now at 180. But I'm sure that about 7 pounds of that is probably fat mass. Donnie?
When you're on bulking cycles, the anabolic nature of it, you're just incredibly hungry. Should you just roll with that, just eat as much as you want?
Yeah, so the question is, when you're on these cycles and you do a whole lot of heavy lifting and you find that you're really hungry, just eat. Just obey that hunger. There's no... I'm much more... The food quality is much more important than food quantity. I'm not saying that calories are absolutely not important. If you want to lean out, you will need to create a little bit of a caloric deficit. But you don't need to worry about calories if someone's metabolism is completely screwed up. What you need to worry about is food quality. You need to fix the metabolic problem before you start worrying about the calories, right? So let's start with the carbohydrate hypothesis. So Ansel Keys kind of let the cat out of the bag. He's like, okay, carbohydrate might be a problem. I see this correlation. So in order to determine what the heck's going on, let's go through a little bit of carbohydrate digestion. So when you eat carbohydrate, this one you really taste, right? The brain detects the sweet taste, and that triggers, again, the cephalic phase of digestion. And that also begs a question. Is it a good idea to be eating things that taste sweet but don't have any calories in them? Right? This is a question that you get all the time. And I get people like, oh, I really like my artificial sweeteners. Don't take those away from me. But there is a physiological response to sweet taste. Your body tries to estimate how many calories are in food by the sweet taste of the food. If you eat stuff that's sweet and doesn't have any calories, is there a detrimental effect to that? Yeah, there is. So a role for sweet taste, calorie predictive relations in energy regulation by rats. So we found that reducing the correlation between sweet taste and the caloric content of foods using artificial sweeteners in rats resulted in increased caloric intake, increased body weight, and increased adiposity, as well as diminished caloric compensation and blunted thermic responses to sweet-tasting diets. These results suggest that consumption of products containing artificial sweeteners may lead to increased body weight and obesity by interfering with fundamental homeostatic physiological processes. These things are really bad. If that's not enough, it turns out that it also changes, at least Splenda does, alter the gut microflora. And this is something that's really important. The population of bacteria and the specific ratio of good and bad bacteria that is in your gut, really, really important. And something that modifies that significantly is probably bad news, assuming that it's modifying it in the wrong direction. And it appears that this is doing so. And you can read that. There's like a bioavailability of drugs that's involved, as well as other things. So artificial sweeteners are definitely a no-no. And they're just going to make you crave carbohydrate. I mean, your body's just going to get pissed off. It's like, hey, you promised me, and I tasted the sweet stuff. You promised me something sweet, and I didn't get it. I want carbohydrate, and you're just going to end up craving carbohydrate all the time. So these people that just can't get rid of the carbohydrate cravings because they keep consuming these things, and you really need to eliminate those. When I first went, fully paleo, I had absolutely no problem with the food choices. But I was a Dr. Pepper addict. I would have like Diet Dr. Pepper, multiple of them, every day. And quitting that was hell. And I started doing more research on that. I mean, how can this be so bad? And it wasn't just the caffeine. There's something, that you're just craving the taste of it. And it turns out that there's all kinds of, those things have no redeeming value, by the way. Diet sodas, there's just absolutely nothing good. The acid really, eats away at your bones. And then it turns out that it's phosphoric acid, so it increases the phosphate content of your blood, which then increases your rate of aging. There's all kinds of bad stuff to that, but it is really hard to quit. So you're going to have, clients that say, man, I really need my Diet Coke, but you've got to get them off the crack. There's no redeeming value to that stuff. So the carbohydrates mixed with saliva forms a bolus, and that the breakdown of carbohydrate begins here with this enzyme that's called salivary amylase. So this is an enzyme that breaks down carbohydrates into their constitutory parts. So the bolus is sent to the stomach, and that triggers gastric phase of digestion, again because of distension. And then any free glucose that's present at this point is going to suppress the hunger hormone ghrelin. But fructose, this other monosaccharide, does not. And as we get into this whole carbohydrate thing, fructose is going to come up more and more, and you're going to see that it's problematic. We're going to point the finger at fructose and say, hey, this might be what's going on here. So there are cells that are lining the wall of the stomach, again, that secrete leptin in response to the meal. That crosses the blood-brain barrier, enters the central nervous system, and it acts on receptors that control energy intake and expenditure. In this case, hey, you've eaten a meal, everything's okay, energy levels are fine and whatnot. Digestion of carbohydrates doesn't occur to a significant extent in the stomach because the salivary amylase is deactivated by the digestive enzyme. So again, most of the digestion of carbohydrates happens in the gut. In fact, most of the digestion happens in the gut, really. With protein, the hydrochloric acid in the stomach doesn't do a whole lot. But there are enzymes like trypsin, chymotrypsin, and whatnot that do a pretty good job. So the chyme, again, which is the mixture, that's released into the duodenum. That, again, triggers cholecystokinin, right, which suppresses hunger. And that also stimulates these pancreatic amylase now, and then from anciner cells, the pancreas. And this breaks down carbohydrates into oligo and disaccharides. Then it goes further into the GI tract, and there's what are called brush border enzymes. These are enzymes that are in the intestinal layer near the enterocytes, and they have alpha-dextranase in combinations with lactase, maltase, and sucrase that degrade all of this stuff to monosaccharides. And those monosaccharides are absorbed by the villi on the enterocytes, and it goes straight into the bloodstream. So amino acids and carbohydrates can go straight into the bloodstream. I should say monosaccharides. Not going to cover protein digestion. I wish I could because it's really important, but I just don't have the time to do that. So the monosaccharides are absorbed by the blood vessels in the villi. Again, that releases PPY, but it doesn't release a whole lot of PPY. Proline and fat release more PPY. And again, PPY is this hunger-reducing hormone that acts on the CNS, the central nervous system. So the monosaccharides enter the bloodstream, and once in the bloodstream, glucose is going to stimulate secretion of insulin by the pancreas. Fructose, on the other hand, doesn't do that. And fructose doesn't do that because fructose can only be metabolized by cells in the liver. And every time I say that, so some people are like, yeah, that's not true. Not entirely. Sperm cells can also metabolize fructose. But before you go out and binge on fructose, improve your fertility, you might want to listen to this whole lecture because it's not going to improve your fertility. But yeah, fructose can be metabolized by sperm cells to a certain extent, but mostly by cells in the liver. So because your body can't, the cells in your body can't really process it, then there's no secretion of insulin that occurs. But in order for carbohydrate and amino acids to enter the cells, you need insulin. And that's because insulin binds to either fat cells, which are called adipocytes, or muscle cells. So here's the insulin, which is this little sphere here, and that binds to its receptor. And it activates something called GLUT4. And then by GLUT, I don't mean the muscles. GLUT here is short for glucose transporter. And there's multiple versions of these. This is glucose transporter 4. So the insulin binds to its receptor, activates GLUT4, and then GLUT4 brings the carbohydrate into the cell. The metabolism of carbohydrate by adipocytes actually causes the secretion of leptin. So this is essentially your fat cells saying, hey, we're fed, we've gotten some carbohydrate, and every energy stores now. And if the brain reads that signal, then all is good. So there's an enzyme called hexokinase that's in most cells. So when glucose enters through GLUT4, hexokinase then phosphorylates glucose at the 6th position, and it makes something called glucose 6-phosphate. This is essentially a way for the cell to put a leash on the glucose and say, you're staying right here. So once the glucose enters the cells, it cannot leave. There are only 2 organs that can secrete glucose back into the bloodstream because they have an enzyme that can dephosphorylate it. Those 2 organs are the liver and the kidneys. So once glucose gets stored into the muscles, it doesn't come back out. So let's say you're running a marathon and most of your energy is spent, by your legs, like the glucose, the glycogen that's in your legs can't feed your arms, or the glycogen that's in your arms can't feed your legs. It's local. So that's why you need some glycogen in the liver such that it can be released throughout the body in the bloodstream and feed your other muscles. So in fat cells, like I said, most of that goes to the Krebs cycle, or it goes to de novo lipogenesis for making fat. And then in the muscle cells, the glucose 6-phosphate gets isomerized to glucose 1-phosphate, and then that gets stored as glycogen. Now, all of the glucose that is not utilized, it turns out glucose is a universal fuel. All the cells in your body can burn glucose for fuel, right? Whereas only the cells in the liver can process fructose. So if there's some glucose left over at the end of the day, that's eventually going to make its way to the liver. And all of the fructose that you ingest is going to make its way to the liver. So what happens? Well, remember there was an insulin release because we ingested some carbohydrate, mainly glucose, and that insulin binds to a receptor at the surface of the liver, and it sets off a whole cascade of events. So there's something called IRS1, insulin receptor substrate 1, and that gets phosphorylated at a tyrosine residue. So what that means is that there's a specific monkey in the chain that's called tyrosine, and this thing comes over and it tags it with something called phosphate. A lot of biomolecules can be modified at the surface with either sugars, phosphate, methyl groups, or acetyl groups. And this is essentially a way to communicate with the body, saying, okay, this is what's going on with this molecule, I'm reading that, I'm going to do this with that. So it's kind of a communication system. So when this happens, AKT is then expressed, and then this activates SREDP1, which is sterile regulatory element binding protein 1. And this activates glucokinase. That is the hexokinase equivalent of the liver. So this is the thing that puts the leash on the glucose in the liver. And it also activates 3 enzymes: ATP citrate lyase, acetyl-CoA carboxylase, and fatty acid synthase. Those 3 enzymes are part of a process called de novo lipogenesis. That literally means new fat creation. Okay, so essentially the binding of insulin to the receptors on the surface of the liver, just like turning the key, it's like, okay, you're ready to process carbohydrate now. That's what this means. Glucose will enter the liver via receptor called GLUT2 via protein, actually called GLUT2, whereas for fructose, it's GLUT5. And there's something really interesting with fructose. Fructose does really something interesting to the liver. When fructose enters the liver, it activates glucokinase further. So it increases the liver's phosphorylating ability. Essentially, it turns your liver into a sugar sponge. The liver already has a significant capacity for phosphorylating fructose, but it even increases the capacity for glucokinase, which means that this glucose 6-phosphatase, what allows glucose to leave the liver, is going to be outcompeted by glucokinase. In fact, when glucokinase is highly activated, there's no sugar that leaves the liver. So your liver gets turned into a sugar sponge. We'll see that might be a problem. This is essentially a breakdown of what I've talked about, and we have all the information that we need now to kind of look at, very superficially, if you will. There are details that I'm skipping here. Like I said, I can't go into that much detail. But what goes on when we eat a specific meal and when we're in a specific metabolic state. So let's say that I've got someone whose liver glycogen stores aren't full. So that happens when either you have adequate caloric intake, you do physical activity, especially high-intensity intermittent training, or you're on a low-carbohydrate or ketogenic diet. When you're under those circumstances, either a combination of those three or one of them, your liver glycogen is probably not going to be full. So we've got someone whose liver glycogen isn't full, and they're going to eat a serving of a food that's mostly glucose with a little bit of fructose. So let's say a sweet potato. A sweet potato has about 1 to 2 grams of available fructose and 22 grams of glucose per 100 gram serving. So what happens when we do that? So this gets complicated very rapidly. Everything that's orange in here is an enzyme, and everything that's blue is a substrate or a product. I'm putting that there, like I said, for additional information. You don't need to know all of this to understand what's going on. But the fructose enters the liver, activates glucokinase, phosphorylates the glucose, and the fructose follows this pathway over here, making glyceraldehyde and dihydroxyacetone phosphate. This is called DHAP. And this stuff goes all the way up here. Notice the arrows. It can go forward or backwards, makes its way all the way up here, and quickly replenishes liver glycogen. There's some of it that might make its way down here to the Krebs cycle and be used by the cells for energy. So when we're dealing with carbohydrate, remember I mentioned earlier, you don't need beta oxidation. You burn the stuff directly in the Krebs cycle. So, it doesn't look too bad, right? And this is just a summary of that. So it turns out that when your goal is to fill or replenish liver glycogen, fructose is somewhat beneficial. It's a nice tool to use. Now, we could argue all day about the ratio, what should be the ratio of fructose to glucose, but one thing's for sure is that it is beneficial under certain circumstances. We'll see that it's detrimental under others. So the problem with fructose is that it fills up liver glycogen really quickly. So let's look at what happens in the fasted state. So like I said, these things can go forward or backwards. And in the fasted state, if there's any fructose in the bloodstream, it's going to get absorbed, and it's going to get turned into alpha-D-glucose 6-phosphate. Once that happens, the fructose no longer activates glucokinase, so sugar can now leave the liver. The glycogen stores are going to be tapped. This is going to go in reverse and also going to make some alpha-D-glucose 6-phosphate. It's going to be dephosphorylated, and it's going to be released in the bloodstream, and that happens via the action of glucagon. So essentially, when you're in the fasted state, you have glycogen stores in your liver that act as a source of sugar, and the body just releases that to feed your cells, most importantly, the brain. And this is just a summary of that when you're reading that on your own terms. So now let's look at what happens when, let's say, we ingest a large, calorically dense, carbohydrate-rich meal that contains a sufficient amount of carbohydrate to completely fill liver glycogen and a sufficient amount of calories to create a hypercaloric state. In other words, a bender. You go on like a pizza and beer, or you hit the ice cream bar or something like that. 3 pints of Ben & Jerry's ice cream. What happens when you do that? Things get really complicated now. So what's going on? Well, like I said, the fructose and the carbohydrate, they're fairly quickly going to fill up liver glycogen. So substrates are going to have to find another way to leave the whole system. And what's going to happen is the fructose is going to come down, and this glyceraldehyde is going to get turned into glycerol, and then some of the excess glyceraldehyde 3-phosphate is going to enter the Krebs cycle. It's going to get transformed into pyruvate, but the Krebs cycle is going to overflow. So this is like a lake. There's a river feeding into it, a river feeding out of it. The river that's feeding into it is just going faster than the river that's leaving it. So the lake overflows. So something has to come out. The substrate that comes out of the Krebs cycle is called citrate. Right? And this is where I say I'm simplifying things. The citrate is going to enter de novo lipogenesis, and here you have this de novo lipogenesis enzymes and ACC. I could talk about the fact that adiponectin actually has an effect on AMPK and SIRT1, and SIRT1 is actually involved in intermittent fasting and whatnot, and AMPK is involved in the activity of ACC and de novo lipogenesis, and you keep going round and round, and people's heads are spinning like, oh my God, I just wanted to know what to eat to improve my performance and lose weight. Why am I listening to this guy?
What are your thoughts on cheat meals then?
So I'll get to that. Yeah, I'll get to that. So the question was, what are your thoughts on cheat meals then? That's always the question. So citrate leaves the cycle. It gets transformed into acetyl-CoA, then malonyl-CoA, then something called palmitoyl-CoA. And this is essentially a saturated fatty acid. It's palmitic acid that's bound to a substrate called coenzyme A. When you overeat carbohydrate, your body synthesizes specifically one saturated fatty acid, and that saturated fatty acid is called palmitic acid. All right? And because we have plenty of fructose around, we have plenty of glycerol, all of this is packaged into triglycerides, it's packaged into VLDL, and it's sent out. The liver ships it out. And what's going to happen to that VLDL? Well, you just ate a really high carbohydrate cheat meal, so your insulin levels are high, which means that the palmitic acid that's in that VLDL is going to get stored, right? That's going to get stored as fat. So you go on a binge from once in a while. The worst thing that's going to happen, you might store a little bit of fat if you happen to fill your liver glycogen. Now, how fast liver glycogen gets filled all depends on, was it depleted, yes or no? It turns out if you take someone that's like really, really depleted, it can take a while to get into to actually activate de novo lipogenesis. We're going to cover an article of that at the very end. So, okay, let's say that you do end up filling liver glycogen and activating de novo lipogenesis. The worst thing is going to happen, you might store a little bit of fat, but then you get back on the bandwagon and the horse the next day, and you're going to burn that fat eventually, and not a huge deal. So a cheat meal from time to time isn't going to do that much damage, especially if you're on a low carbohydrate diet most of the time. Meaning, especially or you're doing exercise. If your liver glycogen isn't always topped off, then that meal is going to do a whole lot of damage. Don't recommend doing it every day. So that begs the question: what happens when we're on a high carbohydrate diet? There's a lot of fructose in the diet, consumed on a daily basis, chronically, for a prolonged period of time, in a sedentary, hypercaloric state. In other words, what happens in the typical North American person? Right? 60 to 70% of calories from carbohydrate, no exercise, and a lot of fructose. What's going on? So remember, fructose quickly replenishes liver glycogen. It doesn't suppress ghrelin. It doesn't stimulate insulin or leptin secretion. And here's a paper on that, just to support that notion. Dietary fructose reduces circulating insulin and leptin, attenuates postprandial suppression of ghrelin, and increases triglycerides in women. And I always have some dude at the front that's like, yes! And no, it was tested in women, but it happens in men too. It doesn't mean that men can eat all the carbohydrate or fructose that they want. So, under those circumstances, glycogen most of the time is full, so a lot of stuff is going to end up in this de novo lipogenesis pathway. That means you're going to be making a lot of palmitic acid, and a lot of palmitic acid is going to get shipped out as VLDL. What are the consequences of that? Well, to start, if you're on a 4-week high fructose diet, These are overfeeding studies, by the way. They're feeding these people really high quantities of fructose. So this is more like of an acute study, but they're trying to see what would happen if you're doing this on the long term in a chronic fashion. But what happens with a 4-week high fructose diet? Well, your VLDL triglycerol increases, lactate increases, glucose in the blood increases, and leptin increases. Why does leptin increase? Well, like I said, the fat stores are increasing, so the fat's trying to tell the brain, hey, you got enough energy, stop that. Just stop the carbohydrate binge. There's enough energy. I don't want it anymore. So we see here the beginnings, triglycerides are increasing and stuff like that, the beginnings of dyslipidemia a little bit, right? The leptin levels increase. Is that really bad? Well, it turns out that leptin predicts a worsening of the features of the metabolic syndrome independent of obesity. There's like a direct correlation with the leptin levels in your blood and whether or not you're on your way to metabolic syndrome and other nasty effects in the end. So there's a lot of people that do or that will have like sugar binges because they say it's good and increases leptin. And what I say to that is like, no. You don't want to increase leptin. You want to increase leptin sensitivity in the same way that you want to increase insulin sensitivity. Like having more of that substrate isn't necessarily good. And in fact, in this case, it's telling you that you're heading down the wrong path. So what can palmitic acid do? Well, palmitic acid mediates hypothalamic insulin resistance by altering PKC theta subcellular localization in rodents. What the heck is going on? Palmitic acid is eventually going to make its way to the brain, to the central nervous system, where it's going to bind to this substrate, and it's going to cause leptin resistance in the brain, as well as insulin resistance in the brain. Both of those are bad. You realize leptin is telling your brain how much energy you've got such that your brain can figure out whether or not it needs to eat. If your brain can't hear that signal anymore, it thinks that it needs to eat. So I want everybody to realize here is the mechanism. Here is why certain people are fat and keep eating all the time. It's because there's a metabolic derangement. And this is something that Gary Taubes tries to drive home. He's like, people aren't fat because they're eating too much. They're eating too much because they're fat. That's what he means by that. Right? So it completely changes things around. So some people are like, well, what does that mean for me? One thing that's really interesting, people will say, well, fat makes you fat. My contention is that not necessarily, but it depends on the context. If the metabolism is completely screwed up, then it might. So fructose-induced leptin resistance exacerbates weight gain in response to subsequent high-fat feeding. Right? So they take a group of rodents or people, completely ruin their leptin resistance by feeding them a lot of fructose, then they feed them a lot of fat. And, lo and behold, they get fat. So it makes you more likely to store the substrate.
So when people are more carbohydrate adapted, that essentially means their leptin sensitivity is still quite good, right?
So the question is, when someone is highly carbohydrate adapted, is their leptin sensitivity still quite good? It depends on the fructose content of the diet. Someone who is eating a lot of carbohydrate isn't necessarily on their way to metabolic syndrome. I'm going to cover that a little later on.
So is there a diagnostic for that then to look at the leptin?
Leptin resistance? Yeah, absolutely. Most of the times they're looking at the levels. So is there a diagnostic for leptin resistance? And what they do is that they look at the levels, and if they're really high and your body is not responding, they're like, yeah, just like the article I showed, right? And there might be something's going on, something's starting to happen here metabolically that's not good.
And would that be as far as a diagnostic of someone to figure out if they're better carbohydrate adapted, or someone's athletic, for example, taking more carbohydrates and looking at the downstream implications? Is that kind of a pathway you might want to go through?
So I guess the question is, for someone who's more carbohydrate adapted, do you need to worry about their leptin sensitivity? I'm going to get to that a little later on. Like I said, I'm not about low carb, high carb, or like this type of diet, that type of diet. I'm just going to give a prescription about food quality at the end. And Whether or not you should be high carb or low carb depends on your level of activity in the end, really. So if you've got someone who's training for a triathlete, I'll recommend, they should be taking in carbohydrate. I'd like most of that to be glucose with a little bit of fructose, and we'll see why. So I'll get into the details of that a little bit later on. So here's just a summary of what we've been talking about. There's a lot of people that ask, well, hey, insulin resistance of the brain is, okay, leptin resistance I can understand, but, what does that mean for me? And as a chemist, I get this little magazine. It's called Chemical and Engineering News. And there's all kinds of little interesting tidbits. But there is this article in Chemical and Engineering News in May 18th, 2009. This is the reference. It was called Alzheimer's Scary Link to Diabetes. And a researcher that's being interviewed says the following thing. So what's the bottom line on the link between Alzheimer's and diabetes is the question. And Delamonte, who's the researcher, takes the most radical stance on that question. Alzheimer's disease and type 2 diabetes affect different parts of the body, but they are manifestations of the same disease, she contends. Indeed, she refers to Alzheimer's as type 3 diabetes. Alzheimer's disease is just diabetes of the brain and is being referred to as type 3 diabetes and is being treated very similar way to diabetes. Like just people inhale insulin aerosols. Not very effective, but that's how it's being treated. So, 10 more minutes and then we'll go to lunch. So what else is going on if you just keep doing this chronically over time, a lot of fructose, a lot of carbohydrate, what else can happen in the liver? So this palmitoyl-CoA and one of the substrates from the fructose metabolism, fructose 1-phosphate, are going to activate an enzyme called C-Jun N-kinase 1. That's going to be activated. And biologists have a lot of fun with their acronyms. They tend to create acronyms that are fairly apropos. So the acronym for this is JUNK1. And it's called JUNK1 because it's not good. So fructose-mediated stress signaling in the liver, implications for hepatic insulin resistance. So we propose that in the liver, the mitogen-activated protein kinase C-Jun N-terminal kinase JUNK1 links excessive nutrient metabolism with impaired insulin regulation of glucose production. The liver, by virtue of its anatomic position and selective regulatory features, buffers and is highly responsive to changes in nutrient delivery. In particular, sugars such as sucrose and fructose uniquely regulate and are selectively metabolized by the liver. We propose that when hepatic fructose uptake exceeds requirements for glycogen and energy, the JUNK1 signaling pathway is engaged as part of the adaptive response. So why is that bad? Well, initially I said, insulin binds to a receptor on the liver, and that sets off this cascade which activates glucokinase and the de novo lipogenesis enzyme. Well, it turns out that JUNK1 takes IRS1, the substrates, and it tags it at a different amino acid. It tags it at a serine amino acid, which means that to a certain extent, your liver is now becoming insulin resistant. It is not always properly responding to the signal that it gets from insulin. Some people say, oh, well, yep, there's a question.
Is there a question? Yeah, before we go too far, we got 4 questions online. So the first one is, Matt, based on the explanation around artificial sweeteners at the beginning of your carb section and cheating your body into wanting carbs and even craving carbs, can I assume the same around cheat meals/days and craving carbs again?
So that is a really good question, right? If artificial sweeteners are really bad, what happens during the cheat meals? That all depends on the amount of carbohydrate that's in this cheat meal and something called hysteresis, which is gene memory. So there's this thing in engineering, it's a switch. And let's say from 0 to 5 millivolts, the switch is off. And you go beyond 5 millivolts and you turn on this switch. And then you think, well, if I go back below 5 millivolts, I'm going to turn it off. And it doesn't. The switch stays on until you get close to 0 again. Something very similar happens in your body, and it's called hysteresis. It's gene memory. So if you spike sugar really high and you flip the switch, your body's going to turn to burning carbohydrate more than fat via hysteresis. So that can then cause carbohydrate craving because your body's going to be like, hey, I'm not adapted to the fat anymore. I need some carbohydrate. So if there's some folks in here that when you're hungry, you feel a little lightheaded, your hands start to shake, it's hard to focus, you've got some problems with carbohydrate versus fat metabolism.
Okay, the next question is from Alex, and it's kind of along the same line here. I follow a paleo diet with intermittent fasting, but my coach has me on a weekly cheat day or meal to restore glycogen levels.
Yes.
Okay, so then the next question from Chris.
So, I mean, just to expand on that, sure. Especially if you're doing a lot of Metcon, I really like the ketogenic stuff, but I wrote about this in Rolf Wolf's website. I went ketogenic for like 3-4 months, and I got some really good results with that, but that eventually caught up with me. I was doing a WOD, it was from OPT's website, and two of my weaknesses, I have short arms, some people may have noticed, so I'm not a good rower, and this WOD was like rowing with sumo deadlift high pulls, right? Two exercises that are essentially the same. And it just destroyed me, and it was after essentially 6 months of doing like a really high ketogenic diet and doing some Metcon. And I finished that WOD, my eyes were rolling in their sockets, my eyelids were really heavy, I was falling asleep, and I'm thinking to myself, holy crap, my brain's running out of sugar. So, which makes sense. So my glycogen stores were so low that my brain was running out of sugar. I'm like, okay, there's no grocery stores in the environment. What am I going to do? I hit Ben & Jerry's, the closest one. I sat down at the counter and I said, I want a banana split and 2 pints of ice cream. And I made sure to pick ice cream that didn't have any gluten in it. And I ate all of it right there in one sitting in front of the clerk, who was overweight and just stared at me in awe. That I could actually do that. And that's when I realized that, okay, I mean, there's other stuff that I'm going to cover afterwards. This can mess with like your testosterone and cortisol ratios. But if you're going to do the Metcon, really that post-workout carbohydrate meal is important. It's just like it'll increase the amount of testosterone, it will decrease the cortisol, so it will increase your free testosterone to cortisol ratio, it will improve your performance. So if you're going to do the stuff that burns a lot of carbohydrate, it's nice to have it in there. What's really good is that if you're mostly fat adapted and ketogenic all the time, and you throw in the carbohydrate post-workout, your body's going to realize that stuff is precious, and because it's fat adapted and it can burn fat, it's going to say, oh, okay, the carbohydrate I need to store as glycogen right now, and I'll use the fat for fuel. So you can still keep that metabolic advantage of burning fat most of the time while having the fuel to do the Metcon. Another question?
Yeah, so it's obvious that there's 6 questions now.
Wow.
The follow-up to that, before we go on to the fructose questions, is would a pint or so of whole milk after workouts during a mass gain phase be a bad idea if you're trying to stay in ketosis?
Would a what?
Would a pint or so of whole milk be a bad idea?
Yeah, so I'm going to cover dairy a little bit in the last talk. Dairy is really a gray area, and the problem is that, actually, how about I just address that later, just to save some time.
Yeah, what we could probably do is just give you these emails, and then you could respond back to the participants if you so choose.
Sure, it's just that one I'm going to cover later, so.
Sure.
A little bit of Q&A at the end, right?
Okay, yeah.
Is there any difference between getting fructose from fruit, where the fructose is bound with other sugar molecules?
Absolutely, there is.
HFCS, where fructose
so
is free.
the fructose that comes from fruit also comes with fiber, and fiber slows down the absorption of sugars and limits the absorption of sugars. So if you're getting fructose from like agave nectar, that's a really bad scene, really bad deal. I cannot recommend agave nectar. I mean, it is evil. And then high fructose corn syrup would also be bad. Sugar is just a tad better than high fructose corn syrup because at least the bond between the glucose and the fructose is still there. So yeah, there is a difference between getting it from fruit or like pure sugar, but I still, I don't recommend a lot of it.
So where do artificial sweeteners fit into carbohydrate metabolism and insulin?
Where do they what?
Where do artificial sweeteners fit into carbohydrate metabolism and insulin?
They are not Artificial sweeteners are not involved in carbohydrate metabolism. And then there's this notion that they increase insulin. And like I said, there's this cephalic phase of digestion that gets turned on. If you look at various papers, the insulin secretion in response to artificial sweeteners is tiny. It's really tiny. It can almost be ignored. But the problem is still there and has to do with messing up the cephalic phase of digestion and other things like that.
Okay, final question.
Yeah.
I had an assessment with James Fitzgerald, and he used skin fold calipers to determine that I am carb tolerant. He suggested I try carb loading twice per week. Taking into account this fructose, glucose stuff, what are the best sources for this? Is there a particular time I should be experimenting doing this, like post-workout, before bed, etc.?
Yeah. I would not recommend it before bed because it will minimize growth hormone secretion. So there's growth hormone secretion while you're sleeping. If you eat a lot of carbohydrate, it'll interfere with that. I would definitely try as much as possible post-workout. So, but when you work out, there's this mechanism that turns on called non-insulin mediated glucose uptake, which means that glucose can be sucked into the cells without the action of insulin. Now, it turns out that glucose digestion, it takes about an hour to an hour and a half for the glucose that you ingest to get into your bloodstream. So the window is closed by then. But what really happens when you're having this carbohydrate is that your glycogen stores decide that they can release more glycogen into the bloodstream because they know that more is on the way. And they've done experiments where cyclists, where they can exhaust them completely, have them rinse their mouth with the sugar solution, spit it out, and then they can keep going. And I wouldn't recommend doing that. I would actually swallow it. Because eventually it's just like the artificial sweetener. You're tricking your brain, and it doesn't like that. But the whole post-workout window has more to do with your brain detecting that available nutrients are coming in, and that it can release a little bit more from its stores than it is directly. It's not directly coming in from what you're ingesting at that time. But yeah, post-workout would be ideal for that carbohydrate repletion.